the heat transfer from a rectangular fin, and we assume that the cross section is remain constant. So we have this rectangular fin mounted on a wall, and if we look from this side, so if you view from this side, your wall will look like a vertical line, and this portion we will visualize like this. So this is the length of fin you can visualize. This is length of fin L. So if you visualize this one, you can find the cross section. The cross section is consist of W and T, where W is the width, T is the thickness. So perimeter is 2 times W plus T, and the cross section area is W into T. The heat from the wall will enter by means of conduction. So that itself is called as Q fin. A is minus K multiplied by A, that is AC area. This area is AC area available for conduction. So minus K into AC into dt by dx. You have to solve this at x equal to 0. We are measuring x perpendicular to wall towards fin. So this one is called as x equal to 0. This one is called as a T, x equal to L. So heat enter from this side exactly at x equal to 0. So you have to solve this value at x equal to 0. Over this we will draw the temperature profile. How the temperature will vary with respect to length. So on y-axis we are going to plot temperature. X-axis is the length. Let the fin is surrounded by T infinity as the surrounding fluid temperature. By addition of heat, this temperature will not change, so it remain constant, act as a thermal sink, and the temperature along the fin will vary from the root temperature T0 to TL. But we don't know how it varies, so that you have to solve first. At any distance x, we'll locate the value equal to Tx. So at x equal to 0, you have to label as T0, stands for x equal to 0. At T, you have to write down TL. K is the thermal conductivity, H is the heat transfer coefficient, T0 is the root temperature at x equal to 0, and TL is a tip temperature at x equal to L. So suffix 0, L are given on the basis of x. This is the excess temperature the fin have over the surrounding temperature. So theta is called as excess temperature, normally represented as theta x. Excess temperature is always taken as positive value. So this time is the temperature difference between Tx and T infinity. So we have Tx minus T infinity equal to theta x. So if we write x equal to this theta x, and if we go to this theta x, if we write x equal to 0, we are at the root, that is this value is theta 0, that is T0 minus T infinity. Similarly, we can write down theta L, that is this difference, which is TL minus T infinity. So theta L is TL, it is L minus T infinity. And in differential form, we have to write down d theta x equal to dtx, and the T infinity is not changing, so that derivative will be equal to 0. Now consider here one small thickness of the fin at a distance equals to x and thickness equal to dx. This thickness in the original figure will look like this. So this is the dx. So we will take out this elemental area and try to develop the differential equation over this. So if we develop this surface, so that surface, slightly I am enlarging that figure, will be like this. So this one is a width, that is W. This one is thickness T, and we are considered only dx. From the left face, heat is entered, and from the right face, the heat leaves. So this is qx plus dx, representing the distance of plane from origin. So this plane distance is x plus dx, and this one at a distance equals to x. So this is qx. So along x direction, heat is conducted, while from the rest faces, that is from this face which is perpendicular to y-axis, and the area of this face is w multiplied by dx, there is a convection. So that area is w into dx. Same area is on the bottom side also, so we will multiply by 2 times. From bottom side also heat is transferred by convection. From the area perpendicular to z-axis, this is dx multiplied by t. One area is on the back side, so this is 2 multiplied by dx multiplied by t. From whole this area, heat is transferred by means of convection. For convection heat transfer, Q convection we have area multiplied by H, and at that point we have a excess temperature equal to theta x. So this total quantity of heat is transferred by means of convection, and this sum is same as 2 times Wt if I take out dx common. So I can write down Q convection as perimeter multiplied by dx, that is the area available for convection, multiplied by H multiplied by theta x. And recall that for conduction you have to take area perpendicular to the direction of flow, that is this H area is perpendicular to the heat transfer along x direction by conduction, that is this area, or we can say this area which is W into T, that we called as AC area. So you have to write down Qx according to Fourier is, so it is minus k into A into dt by dx. Now what we do, we apply the law of conservation of energy, that is summation of energy in equal to summation of energy out. As far as summation of energy in and summation of energy out, we have only energy in, that is Qx, and then we have on the right face we have conduction is out and convection is also out. So as far as in is considered, we have only Qx quantity. This quantity is leaving is Qx plus dx, plus this quantity, that is convection heat transfer, is also leaving from the surface. So this is Q convection. Now Qx plus dx you have to expand using Taylor series and consider only first two terms. So we have Qx equal to Qx plus ddx of Qx into distance dx plus Q convection. Now here the first term will be get cancelled. So Qx is cancelled with Qx, and we can replace this Qx with this value, and convection we can replace with this value. So let's substitute and try to form the governing equation. So we have ddx of Qx, that is minus k into A into dt by dx. So we have minus k into A into dt by dx. A is AC area into dx. Convection is perimeter into dx into H into theta x. So this is P multiplied by dx into H into theta x, and this whole sum is equal to 0. So dx and dx is first cancel. We have dt by dx is same as d theta by dx. So we can replace this term by d theta by dx. Hereafter I will not write theta x, I will only write theta, and dt by dx will replace as d theta. Second thing is that thermal conductivity independent of x direction, and even the area we assume as a uniform. So cross section is uniform along x direction and k is also constant. So our differential equation is applicable for uniform cross sectional. So it's not a function of x, that's why we can take it outside. So this dt by dx we can replace as d theta by dx. So we get minus k into AC. Thus this will become second order is d square is basically t. So we write d square theta by dx square plus perimeter multiplied by h multiplied by theta equal to 0. So we want to rearrange this in a standard form. So we'll adjust the minus sign first. We'll get d square theta by dx square minus of p into h divided by k into AC into theta equal to 0. Now we'll introduce here one term so that it will become a standard homogeneous equation. So let that parameter equal to m parameter, and we'll define this m as under root of p into h upon k by AC. So if we square this quantity, you will get pH by KAC. So we can replace this as d square theta by dx square minus of m square theta equal to 0. This is a homogeneous equation. So we have to find out. So right now we have developed this equation using three laws. First is law of conservation of energy. Then we have used the Fourier law. And for convection we have used the Newton's law of cooling. So combination of this equation will get a governing equation for fin.